Okay, here in this video clip, I would like to present two common approaches for model selection. The first one is to choose model selection criterion, the scores. And these are the scores that contain that trade-off between the loss function and the model complexity. The second approach is the cross-validation. So in this clip, I will focus on representing the scores. So the model selection criterion relies on the parsimony principle that also the same concept of bias and variance. You want to choose a model that explains the data very well, but to achieve that quality of the model, you try to pick the model that has smallest number of parameters as possible. Okay. So the model selection criterion typically contain two parts. All right, that emphasize on the two concepts. The first part is the loss function that indicate the model quality. The loss function can have examples of likelihood function, residual sum square, MSE, they are the same, or the fit percent. Okay, the fit percent, I pick up this is this indicator because it's in the system identification toolbox. So the fit percent is calculated in this way. Suppose your hat is from the model, all right? The Y is the actual measurement. So this is the error of your model. Y bar is the mean, of your data. So you can think of Y bar as a estimation of a simple model, because in the linear regression you see that if you fit Y with a constant model, all right, if you fit your Y, what would be the best constant that represent my data set? If you calculate this best constant in the linear regression sense, you will see that C is actually a Y bar. So this is kind of, this can be regarded as the error of a constant model. So a constant model is simplest, is the cheapest one. So it serves as a baseline, as a benchmark for comparing with your model. Okay, from this fit percent apart, can you explain from this ratio, from this formula? So the fit percent, the higher the better, or the lower the better?
The higher the better.
The higher the better, because this is the error. You want the error to be less, right? But it's subtracted from 1. Okay. To talk the 50%, can it be negative?
No, I can't. It
Because
between 0 to 1.
why?
It is because using two norm and two norm always give positive number, I thought.
Yeah, but this is positive number. Is this always less than 1?
Yes, Achan.
Why? So it's like error of your model, right? And divided by error of constant model. Is this always less than 1?
Yes, I thought, because error of our model always less than error of constant model.
Okay, you think so, right? Okay. I would say that is typical if you don't make any mistake, if you choose an appropriate choice of your model, linear regression, I don't know, you choose you should a model that is more general than a constant model, then yes, the error, this ratio would be less than 1. But sometimes, I mean, you can make some mistake. You can estimate the model in a wrong way. So what I mean is it might be possible if you see in the experiment that this guy, this value is bigger than 1, which means if this guy is bigger than 1, your fit percent is less than 0. But when you have obtained that results, it means that your model perform worse than the constant model. In that case, something wrong, because it doesn't make any sense. Your model is not actually reasonable. How your model perform like worse than a simplest one, all right? So I would say numerically it is possible, but conceptually it shouldn't occur. That's all I mean, okay? Okay, this example, let me go back to here again. The likelihood function, ping, if you use likelihood function to indicate the model quality, the higher the better or the lower the better? Ping.
The lower the better.
So can you recall the meaning of the likelihood function again?
I'm so bad at it. Oh, I forgot about it, Chat, but
Okay.
something like DT or
Napat. What's the meaning? Likelihood functions. What's the meaning, and what's about its value? You prefer a high value or the low value?
The high value.
Because because
I forgot about the meaning.
Totok. What is the log likelihood function?
It's saying that our estimation likely to be close to the real one. So when it has high.
What do you mean the real one? What's the real one?
And the DGP.
Huh? What's that? The what?
In FX representation.
Oh, everyone seems to forget the definition of the log likelihood. Likelihood function is basically the what? The probability density function of your measurements y that is parameterized by some parameter theta in your model. So if it gives a sense of probability, it's a probability that, okay, when you use such a fixed parameter, the probability that of the values of the measurements y. So if it has a high value, it means that at that given theta, the probability is high. It means that it fits well. Your model using theta, it fits well with that data set, with that measurements. Okay, please review. And even you take the log because the log is increasing. Okay, so using the log or the log likelihood function, it gives the same sense. Okay. What about RSS? You want it to be low or high? Ping. Residual sum squared.
it should be lower than.
Should be low, right? Residual sum square and MSE, they are the same, quite the same. All right, just some minor difference in the denominator. Okay. Okay, that's the first aspect of the model selection criterion, and the second aspect is the model complexity. So this is how you this term, how you measure it, all right? You would say, oh, I will count how many number of parameters in models is, or we can have different ways, or we can have our own definition to count it, all right? And that's different from one model to another. But conceptually, the overall idea is to take into account of these two aspects in the criterion, all right? So I will explain a little bit more when we say, oh, to choose a model. By now you should know that it's about choosing the model complexity, but I give you an explicit example again. Suppose you have an additive error model. Okay, your yi, I is a sample index, all right? This is the true representation between x and y. X is the feature, x is a predictor, theta is a model parameter. Okay, this is called additive error model because the error is corrupt. The error corrupts your representation in additive way plus error. Okay. I assume error to be random variable. It doesn't have to be normal, but yes, I just put some example here. So when we say we choose a model, it means that it could be one of the following choices. It is different from model to another model. So in linear regression, model selection basically means you pick a list of predictors. Okay, model with different degrees would mean using 2 features or 10 features, right? 10 features would be more complex. If you use polynomial model, model selection would mean you select a degree of polynomial function, 2nd order or the 10th order. Or if your G, if this representation is used in the data fitting problem, your G is somehow the combination of some basis function. Okay, so if I have alpha k, gk, x theta, you can think of wavelet decomposition as this way. You try to decompose your true relationship decompose in different wavelet basis functions. All right. So the more term you use here, suppose you use n term, the more term, the more basis function you use, it means that you allow the decomposition to be more flexible. So in this sense, model selection would mean you choose the number of basis functions. So that's one example. The second example is if you use dynamical model. Again, dynamical model means that the representation between input and output is dynamic. Input, output, all right? Sometimes I use X, sometimes I use U. So the output depends on the history of the input as well. This is what we call dynamical model. So when I use this representation, Z basically means both Y and U in the past. T minus 1 indicates the term. Okay. Dynamical model examples, autoregressive or ARX, autoregressive with exogenous term, finite impulse response, all kind of things, the time series models, ARMA, ARMAX, everything, state space, everything. Okay. So in this example, model selection would mean you select order PQR in ARMA model, select order of FIR. Okay. Can someone recall what PQR means? What is P? Ping. What is the order P? Order of which term in ARMA process? Ping.
The order of A of term.
The order of what?
A of term.
AR. What about Q?
Q is the integrate.
Hmm?
The term of integrate.
No. Mm.
So sorry, I confused with Arima. It's the
The what? Hmm?
I forgot it.
You forgot it? Oh, so ARMA or RMAX has three features: autoregressive, moving average, and exogenous term. This depends on the pass Y. Moving average depends on the noise term, and X is the exogenous input, right? So PQR just order of AR, moving average, and exogenous term. So of course, if you pick high values of these three choices, it means that you pick more complex models. Okay. So in this in this concept, as you see examples of the degree that we're going to choose for a model choice, but conceptually, let me call it like overall as alpha. All right, like the list of model parameter, the degree of polynomial, the PQR, everything. Let me like call it in a unified approach as alpha. The alpha is a parameter that indicates model complexities. Okay, so as you vary alpha, everything in these bullets will change, will vary according to the model complexities. So I'm going to use L alpha to indicate that that is the log likelihood of your model at the degree alpha. When I choose a particular choice of model complexity, okay, that is how my log likelihood is this value, is that value, all right? So I'm going to put everything as a function of alpha. Secondly, the prediction error is also a function of alpha. I try to emphasize this. The more complex model, when alpha, it doesn't mean that the alpha has to be high or when the model is complex. It's just there's a relationship between alpha and model complexity. Okay. And of course, when the model is complex, right? Prediction error is supposed to be small in some sense, in the norm sense. Okay. Thirdly, okay, the effective number parameters, I use the notation D. This D is also has some correspondence with the alpha. We come back to this again, how we define it. It's the same D complexity and alpha, the notation I use in the slide. I mean, they are all have the same meaning, all right? D represent how many numbers of parameter is your model. That's the complexity, and that's the same as alpha. Okay. But the reason why I have these three different notations because in some particular example, particular model, there's a specific way to define effective number parameters that I'm going to explain next. Okay, here the model selection scores. The term that represents the model quality in this slide is the log likelihood or the loss function. So the notation V is the loss function we have seen before when we talk about PM prediction error method. Okay, the model complexity will be indicated by D, the notation D, effective number of parameters. So I would like to scan through these selections, model selection scores. There's AIC, AICC, BIC. Okay, first of all, Akaike information criterion, AIC, as a function of alpha. Again, I use alpha to indicate that the model complexity degree. So AIC is a function of -2 log likelihood plus 2D. Okay. Can someone, Napat, which term represent model between these two terms? Which term represents the model model quality?
The first term.
The first term. Okay. Okay. Start with the simple model. The first term is high or low? Napat. If the model is simple.
The first term is high.
Is high. The second term is
low.
Is low. Okay. Ping, if I use complex model and I evaluate AIC, the first term is
The first term is high. For complete model, the first term is high.
Why is it high?
The more complex model, it will be the more fit to the data estimates. So
It fit better.
Yes.
So the -2L should be
high.
-2L. The log likelihood indicate the degree how your model fits the data. The higher the log likelihood, which means is better for the data fitting.
Yes.
But with the negative L. Total.
The first term is low and the second term is high, Ajahn.
Okay. For complex model, it fits better. The model fit better. The log likelihood is higher, but the negative log likelihood should be lower. Okay. So you see a trade-off like between simple and complex one, right? In this model selection score in AIC. What are we doing with these model selection scores? We're going to pick the model. Basically, we're going to pick the alpha, the degree, so that these scores are minimized. When they are minimized, it means that it provides you an optimal balance between model quality and model complexity. Now, let's continue to look at the formula of these three scores. For the second one, corrected Akaike information. The formulas are the same, except what? Except the third one, the third additional term, the green box, in addition to what? To AIC. Okay, now let's take a look at the green term. What do you see in the green term? It tries to account for what is N. N is the sample size, the number of samples in the experiment. So it has the second order, the quadratic in the numerator, so it has more penalized. It has more penalty cost when n is not big. When n is small, right? It contributes more penalty on model complexity. All right. What happened when n is very, very big? Napat? When n is very, very big, what happened to the green term?
Is close to 0.
When n is very big, this term close to 0. So AICC
becomes AIC.
Yes, becomes AIC. All right. So the again, the effects of AICC should be more apparent for finite and small n. That's why it's called corrected. Corrected basically means sample corrected. It takes into account small samples. For BIC, what's the difference? What the difference from the first two scores? That is the model complexity term is d times log n. Okay, instead of the factor 2 in the factor 2 here, it has the factor of log big N. Okay, so all these three scores, they have the common ground that it trade-off between model quality and model complexity. The first three scores are based on the log likelihood function, okay, in the first term to indicate model quality. Now, let's take a look at the three remaining ones. The fourth one is Akaike's final prediction error criterion, or FPE. Okay, now take a look at this score. This is your loss function. Your loss function. Remember in PEM, your V can be a trace of the sample covariance matrix, or can be determinant of your covariance of the error. Okay, so this V, the higher the better or the lower the better? Ping.
With this one, the lower the better.
Okay, so for the simple model, the is gonna be, yes, I mean for this V, the lower the better. Okay, so for the simple model, this V would be big, right? This V would be big. Now you see that now the model complexity, the effect of model complexity is seen in the red box. Okay, D, because D is the effective number of parameters. So in this score, what do you see? When the complexity is low, what happened in the red term? Napat.
It's small.
It's small, right? When D is small, like this ratio compared to 1. So this term is small. All right. And again, complex 1, your what? For complex 1, the loss function would be low, right? But then the term in the green, the red in the red box would be higher. But the thing is, the influence of the model complexities, it's seen through multiplicative form instead of addition. In the case of AIC, AICC, and BIC. Okay. So FPE is a score that available in the system identification toolbox as well. It's actually proposed by Professor Lung, who wrote a system identification toolbox. Oh no, actually, sorry, it's Akaike FPE, right? But Lung has proved some properties of this FPE score. Okay, now I would like to represent the last two ones. These are model selection scores that commonly used in linear regression model. The Mallow CP coefficient. Okay, this score again consists of two terms. The first term represents a residual sum square. This is model complexity. The second term, okay, you have D here. So the green term represents model complexity. Adjusted R square. Adjusted R square. It has a model complexity indicator through RSS, but it also take into account the model complexity in D. Okay, so usually when you have, again, a simple model, so the green term would be pink.
The green term would be high.
Should be high. What about the yellow term?
The yellow term low.
The yellow term is low, but maybe I label the whole thing. I label n minus d minus 1. So the yellow term would be
high also.
Would be, yes, like high. So it means that, now, okay, but maybe compare with the complex one. Okay. What about the complex one? Totok, the green term would be
Low.
Would be low. What about the yellow term?
Will be high.
Yellow term would mean n minus d minus 1.
Oh, yes, will be low.
Right? So you see that, okay, and what do we do? What do we do with the green and yellow? Like this is the ratio, right? So it means that if you don't have the yellow term, if the score doesn't take into account the model complexity, all right, RSS will be always decreasing as the model is more complex. But then you adjust this score so that it has a ratio, it's a ratio of RSS to the yellow term. And that's why as you vary the model complexity, when the model is complex, but it's kind of introduce this term to be big, so that it's not worth anymore in terms of reducing RSS. You know what I mean? Like when the model is more complex, even though the RS is lower and lower, but also the denominator is also lower. So the ratio could be, I don't know, it could be bigger at some degree of model complexity. Okay, maybe we take a look at the graph so that you can see the kind of the explicit effects of using these scores. Okay, in this example, I represent model linear regression, and what do we do? The data points, the true representation is the graph of x sine x, which is in the black line. Okay, this is a model setting. When the noise is corrupted, the data points are represented by the red dots. In the model, I try to use something kind of Fourier series. All right, I represent y as a decomposition of sine and cosine at different frequencies. Okay, I vary from k, starting k from 1 to n, but I also vary n. Okay. So so in this setting, a complex model would mean, what does it mean? Ping.
What would mean, the complex model mean?
Yeah, would mean. When I characterize the model in this way, okay, I have these choices, okay. What does it mean by choosing a model in this context, in this example?
I don't understand.
Napat.
The complex model is mean n is high.
Yes, n when n is high. All right, because in this representation, I represent my y as sinusoidal at different frequencies. If I use more numbers, if I use higher number of n, it means that I decompose my signal as a sum of so many frequencies. I allow like more frequency components in the signal y, right? So choosing model basically means in this context choosing an appropriate number of small n, and I vary from n from 1 to 20. Okay. Okay. In this example, now let's take a look closely. What are the model parameters in this model? Totok?
AK, BK.
Okay, AK and BK. Okay, Totok, if I pick a number of n, for example, how many model parameters? For if I just choose a singular value of n, like for example, n is 10, how many parameters do I need to fit for this model?
2 times 10, 20 parameter.
Yes. So the number parameter is 2n.
Yeah.
Okay. So in this example, I choose the effective number parameters to be 2n, d equals 2n. So I'm going to calculate all of these scores from this slide, all right, using d equals 2n. So do you think what technique can I use to estimate the parameters from all the methods we learned? What estimation technique can we use? Ping. Ping. Napat.
Least square framework ก็ได้ครับ
Yes, it can be least square, right? So I hope you can recall, of course, when you use least square, these can be evaluated from the results, right? After you fit. So the parameter alpha here, basically, it means that alpha 1 would mean, when you use n equals 1, for example, right? When n equals 1, your d is 2, for example. At the second degree, n equals 2, which means your d is 4, things like this, all right? You can compute residual sum square at different degrees. And for the score based on the log likelihood, you can assume, recall that the log likelihood can be derived only when you need to assume statistical distribution of random variables in the process, which means you have to assume in some way. You can assume that your E is normal, right? When E is normal, then try to derive the log likelihood and evaluate these scores. We will come back to the details of this evaluation, but here I just would like to represent some results. When you calculate AIC, okay, so it's gonna be like when n equals 1, you get AIC 1, right? And n equals 2, you get AIC 2, and so on. When n equals 20, you get AIC 20. Okay, and what do we do with these scores again, Totok? After we vary the model complexities, what do we do with these scores? We pick the model.
Yes, we compare and we choose the lowest one.
We pick the order that achieve the minimum AIC. Okay, but let me let's say, you pick the AIC, like you, of course, from the numerical values, you can calculate the minimum one. Okay, but then I can also subtract the minimum one from all the scores, right? And I call it delta AIC1, delta AIC2. Okay. All right. So the model that that has the minimum AIC would be the same model that has the minimum delta AIC. Right? I just kind of shift the score. Everyone understand?
Yes, อาจารย์
Okay. Because when we go through the detail of this score, you will see that because AIC based on the log likelihood. And when I express the log likelihood as y1 until yn, right? If you go back and review the concept of log likelihood, you will see that the more samples we use, the value of the log likelihood function will be added up, right? Because it's a summation of the likelihood function of yi. So the magnitude, the scale of these scores depends on the sample data you use. So when you subtract it by the minimum, it kind of like scale down the score. That's why in the computation, in the experiment, it would be kind of convenient to represent the delta of AIC and BIC. Now let's look at the graph. Okay, if I go to this one, this is the score, model selection score based on the log likelihood. Okay, from this graph, yellow, orange, and blue one apart, can you suggest? Okay, AIC and AICC, what model? Can you kind of approximate it from the graph? What model order did they pick? This is the number predictor. This is the n.
I picked the orders.
Not you. This is the score.
Yeah. The order 7.
Order 7. You mean by which score?
By the AIC and delta AIC and delta AICC.
IICC. What about AIC?
If consider only AIC, the order 15.
Yeah, AIC pick like this order. What about BIC?
Order 4.
There's somewhere around here, right? So from this score, you see that AIC tend to pick higher order model. AICC pick kind of a moderate one, but BIC pick the lower model. Okay, this is what we observe. What about adjusted R-square? In this graph, I plot adjusted R-square and compare to the R-square. Let me mention that R-square is basically R-square is 1 minus residual sum square divided by total square. So R-square doesn't take into account the model complexity. Okay. And if you look at the graph, the orange curve, what do you see in the R-square? Is it increasing? Is it always increasing as the model is more complex? Does everyone know that R-square approach 1, which is the perfect fitting? This is in the linear regression, all right? So in the R-square, it's always increasing. What about adjusted R-square? What do you see, Totok?
In some point, it also decreased. For example, the next number 2, it's decreased.
All right, but if you're going to use adjusted R-square as a model selection score from this graph, what model order does it pick?
Number 4.
Number 4?
Oh, the best one is number 15.
The number, you pick the model that has the highest or the lowest value adjusted R square total?
The highest value.
The highest value. You said 13? Okay, it's somewhere around here. But you see, after the order 15, right?
Yeah, 15.
Did you say 13? 15. After at the model 16, it tends to drop a little bit, right? Drop. Okay. And what about the mellow CP coefficients? You pick the model, the best model is a model that has the minimum CP, which is order around, I'm not sure, maybe the graph is not clear. Okay, I have to look at the result. Oh, it peaked 7, all right, because the scale is very close. And now I plot test and train MSE. From this graph again, train MSE is always decreasing, but the test MSE start to rise again at some point. At which point, Ping?
At 0.4.
Around 4, maybe 4 or 6. We're not sure from the graph, all right? We have to take a look at the number. Okay, so from this graph you get you get some idea how these model selection score work. It depends on the model description. So it depends on the score description. AIC, AICC, BIC, and FPE, right? I mean actually the first how many? The first 5 ones, we pick the model that minimize these scores. Only for adjusted R square, we pick the model that has the maximum adjusted R square. Okay. In this, let me just explain one more experiment. Now we pick, this is example of how you pick the order of time series model, the AR. I vary the order to be 1 to 20. This is to fit AR model to unemployment rate time series. Okay. Okay, in the model, in the AR model, YP is Y1, YT minus 1, dot, 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 AP, YT minus P plus noise, right? So this is the AR model of order P. Okay. What are the model parameters, Napat?
A1, A2, and till AP.
Okay, Ping, what does it mean when we say model selection? What do we select in this example?
In here, we select the number of P.
Okay, right. The model selection in this context is to choose an appropriate order of AR model. Okay, so if we add a certain value of P, okay, how many number of parameters total?
P number of parameters.
Okay, so when with the AR model, the effective number parameter is chosen to be P, right? Because that's a kind of a straightforward. We have P parameters, effective number parameter should be P. Okay, and we do the same. We compute model selection score, FPE, train MSE, and fit percent. The data sample is 245, but then in this experiment, we examine in 2 cases. The first case is we're going to use up all the data, use all the 245 samples. And the second case is we going to use only half of it. All right. Let me, I think, okay, all the scores here I evaluate on the training data set. Okay, so the left one, I use all the data. This is the score. This is the score based on the log likelihood. All right. Okay, if we focus on AICC, all this score. Napat, do you see the same, kind of the same pattern that the BIC picked the lower one and AICC picked the higher order score? Okay, can you describe this result? Can you describe the result? Which order was chosen from, you know, each of the scores?
Yes, the first two have the same pattern and has had the same minimum, and in other hand the BIC.
What do you mean say minimum? Maybe you can describe. Okay, AIC peak.
Yeah. AIC peak order 13.
13. Okay, what about AICC?
AICC is 10.
Yeah, we don't know because I mean the scale seems very close, but somewhere around here, right? Okay, what about BIC?
BIC the order 2.
Order 2. All right. It kind of similar to the previous experiment that BIC tend to pick a lower order model, but AIC and AICC seem to pick a higher model. Okay. Now I would like to switch. I still take a look at the model selection score based on the log likelihood, but now I focus on the second case when I use less number of data samples. So Top, can you read the graph? AIC peak.
Yes, from this graph, AIC pick order 13.
Okay. AICC.
AIC picks order 5.
Mm-hmm.
And the last one, BIC pick order 2.
Okay. Now, what is the change you notice from this experiment, from this case?
Between AIC and AICC.
Okay, it seems that the only thing we notice is AICC. Initially, it tend to pick maybe 10 or 13. I need to look at the answer. Okay, all right. Initially, it tend to pick 13 order, but when the sample is less, it picked the 5th order. Okay, so this is the result. I want you to notice that AICC, because the idea of AICC is try to compensate the sample size that is low. So in the score as you see, okay, maybe go back. When n is moderate or small, it penalizes more on the model complexity because you see that kind of the d square here on the numerator. That's why when the sample size is less, now it picks lower order model for AICC. Okay. Now we go back and we see another choice of model selection for FPE, which is the blue line. Okay, I think it peaks around here. Okay, the fit percent. What what model order was chosen by the fit percent? If you just look at the fit percent, what model is best in this aspect? Napat?
The 20th order model.
The 20, right? The most complex one. What about the train MSE? Totok, if you just look at the train MSE, what model is best in this sense?
Also 20 order.
20 order. And you see, 3% and train MSE only cares about model quality, right? Both of them are not concerned with the model complexity. So these two guys are not a good indicator for model selection purpose. All right, that's the conclusion because it's gonna always pick with the most complex one. Okay, now what else? Okay, that's the main message of this experiment, right? Oh, that's about the time.